All right, here we go. This is number 19 in chapter 4 of the Halliday and Resnick book. And actually, if you have the solution manual, you'll notice that they solved this problem as though this position was 40 meters instead of 4 meters, and so their answer is not correct for the printed problem. I'm guessing that the 4 was supposed to be 40, but anyway, so here's the correct solution. Sorry, to be clear, the answers that I posted are correct. It was in Halliday and Resnick's solution manual that was wrong. Okay, so it says the acceleration of a particle moving only on a horizontal xy plane is given by, and we've got this acceleration vector up here. All right, and then it tells us at time 0 what the position is, and it tells us what the velocity is also at that same time is 0. All right, and so what we're trying to do is we're trying to figure out the position vector and the direction of travel after 4 seconds. Okay, so here's what we're going to do. We've got the acceleration. Now notice in number 18, if you just happen to watch that one, in that problem, the acceleration was constant, so we were able to use our constant acceleration equations. This time, the acceleration is not constant. Look, it's got these t's in there, so that means that the acceleration depends on the time, so the acceleration is not, in fact, constant. Okay. Now, we need to figure out where it is for A, and in B, we got to find out the angle of the direction of travel. So the direction of travel is going to be determined by the velocity. So we need to find the velocity, and then we need to find the position. So we learned earlier this year that if you're given the acceleration, you can always find the velocity by taking an integral, right? So here's what we're going to do. I know that the velocity at time t is the integral of my acceleration at time t with respect to t, right? So for us, this is dt. So for us, that's the integral of 3ti plus 4tj, all with respect to t. So when you integrate that, we got to increase our power up to 2, which means we're going to end up with 3/2 t squared in the x direction, and then 2t squared in the j direction, plus whatever our initial velocity is, right? Oh, but it tells us the initial velocity, right? So we should be able to plug this in. Let's see. So that's going to give us, when I add in my I component, I'm going to get 3/2 t squared plus 5.00. So there's my velocity at time t. So that's in the I direction. And then in the y direction, I'm going to get 2t squared plus 2.00 j, and this is all in meters per second. Okay, so I can actually answer question B right now, can't I? I know my velocity vector, depending on t, is this. So let's find our velocity after 4 seconds. So I'm just going to plug 4 into this equation. So let's see. T squared is going to be 16. 3/2 of 16 is 24 plus 5. So I'm going to get 29 meters a second in the I direction just by plugging in 4 for my time. All right, and then I got to also plug in 4 in my time over here. So I'm going to get 4 squared is 16 times 2 is 32 plus 2 is 34 meters a second in the j direction. Okay, so now to find my angle, I need to draw out this vector triangle. So let's see. My horizontal velocity at this instant is 29 meters a second. My vertical velocity at this instant is 34 meters a second. And what I'm looking for, here's my velocity vector. I'm looking for that angle. So I'm just going to use inverse tangent, and that'll give me 49.5 degrees. Okay, so there we go. So now the next thing we got to do is figure out what the position vector is at that same time. So, whoa, that is not what I wanted to happen. Oops. All right, that'll do. I think that gives us enough room. All right, so now to find the position vector, well, remember, we know that position is the derivative of velocity, right? So here we go. Our position at time t is going to be the integral of the velocity at time t with respect to time. So that is the integral of this velocity vector that we had. So it's 3/2 t squared plus 5 in the I direction plus 2t squared plus 2 in the j direction, excuse me. All right, and then this is all with respect to time. So I'm going to integrate this mess. So let's see, my exponent needs to go up to 3, so it looks like I'm going to end up with 1/2 t cubed, right, plus 5t plus some beginning x position, right, plus 2/3 t cubed. Oh, I don't like my 2/3. Oh, wow, that's even worse. 2/3 t cubed plus 2t plus our starting y position, right? Okay, now to be clear, I separated these. This is sort of my, this and this is my r naught, right? My starting position. And instead of just writing r naught, I wrote it in terms of the two components. Oh, this is wrong. What did I forget? I forgot my little vector guys. There's my I, and this is all j. This is not to the exponent. That's just me squeezing it in. Well, whatever. You get it. Okay. So there is my position vector. Let's see. Oh, now I know what x naught is, right? X naught is 20, and y naught is 4. So this is 1/2 t cubed plus 5t plus 20 in the I direction, and then 2/3 t cubed plus 2t plus y naught is 4 in the j direction. Okay, so now all I'm going to do is plug in my time of 4 seconds, and then I think we're done. So my r, my position after 4 seconds, is, let's see, so 4 cubed is 64 divided by 2, so that's going to give me 32 plus 5 times 4 is 20 plus 20, so that's going to give me, what, 72 meters in the I direction. And then if I go over here and plug in 4, 2 cubed is 64, 2/3 of 64 is, well, I'm going to grab a calculator, it's early. So what do we got? 64 times 2 divided by 3. All right, so you get like 42.7 plus 8 plus 4. So 42 plus 12 gives you 54.7. All right, and there we go. There's our position vector in unit vector notation. All right, cool. Hope this was helpful.